2 years back, I chose mechanical engineering as my career option. And I think the reason behind it was this spark inside my head to convert my ideas into something that I could interact with in real life. And I think it was the same for millions of people before me that has now made it possible that we are surrounded by our very own creations, the machines. And the process that makes it all possible of including all this into the reality is called manufacturing. Now, once I got into college, I thought, why do we have such conventional processes where we reduce the entire block of metal into this required product of such a small size? Or, think about casting, where we need to melt the entire metal, then pour it into the molds, and then machine it further. Why can't we do it the way nature does it? Go from the base to upwards, layer by layer, just like the trees that grow from the soil. And that's how I was introduced to additive manufacturing. I am Manas Vyas, and I am a sophomore at the LNM IIT Jaipur, India. And the topic of my presentation is a thematic analysis of additive manufacturing for space applications. Now, before we go towards what this process actually is, we need to understand, why do we even need this? Why should we even move away? So, first of all, we need to understand what industries want. Industries are moving towards lean engineering, which is aimed towards reducing the amount of wastes. And that is a method to realize that is by value stream mapping, which is a graphical method to segregate out the processes in the manufacturing line which create waste materials. Hence, since additive manufacturing is a compact process without much steps inside it, it works towards lean engineering. Second, we need to design for performance instead for design for manufacturing. Design for manufacturing is limited by the constraints of the designs that we can't make, while AM allows us of making complex designs. The third, we need to reduce the bulk. We need to, shed the weight out of our existing machines, and for that, we can utilize AM. Now, let's talk about the process in itself. Additive manufacturing, in a nutshell, is a process where we go layer by layer and create the component instead of subtracting it from a huge chunk of block or pouring it like casting. Now we know what AM is. We need to talk about what are the various AM techniques that are in place right now. I have focused on metallic AM applications since right now they are the most widely used. There are two methods. First of all, go with the powder bed fusion, where the material is in the form of powders which is already there, and you use a laser or electron beam to that is concentrated on the powder to fuse the particles and then go layer by layer. Or the second one, where the material is deposited along with the energy in the form of laser, electron beam, or arc like we do in welding, and then proceed with it. So the next slide is about the materials. So the material vary by the application or the use and even the availability of the component. Also, the materials can be categorized into three main groups: metal and alloys, polymers and plastics, and the new one that you might be really, you would be really interested about it is called concrete or regolith. Now this one, given the credits for it, I've taken it from a site called Science Direct, and I've given the particular references in the reference section in the end. I would like to thank the researcher for this, because using this I would like to explain how an entire experiment is conducted for AM currently. We have titanium aluminum 6v4, which is used in aerospace industry right now on a wide scale. And over here, as you can see, there's this nozzle where the inert gas is getting there for shielding to prevent the material from oxidation, the laser in between, and the material being deposited at the same time. Now we need the feedstock, that is powder material, which can be made from a process called gas atomization, which the people who are unfamiliar, in this process, there's a small opening from which we direct the gas at high amount of pressure, and then melted metal is poured over it so that the material gets broken up into smaller pieces. And after you've done your entire process, you analyze your product. So how do you do that? You try to understand how the microstructure is. So you need to understand what the grain type is, it's long or not, because that's going to influence its mechanical properties. And the second testing is where you apply force on it, put it into different conditions, see how it reacts. And as you can see in the graph, what we inferred from it is that the materials that are made using the additive manufacturing are even better and even stronger than the materials that are produced by conventional process like forging. Now, materials like I told you about concrete or regolith. So, European Space Agency has an idea where we can make based on other planets or in Moon itself, where using the regolith over there, the soil over not soil actually, it's called regolith only. Over there, we can make homes. So, it's pretty amazing. Just think about it. Currently, you can in situation like Corona, you can make immediate houses for isolation using this process if you don't have, if some country doesn't have shelters. The third would be plastics, where plastics are recyclable. They can be used on really wide scale. So, and you can see 3D printing almost everywhere around you right now. And even we have 3D printers in space at ISS, where a company called Made in Space has worked with NASA to make it possible. Then they are testing 3D printing right now. And they're even recycling the plastic over there by melting it and then again using it. And as you can see in the picture over here, what NASA has planned to do is that a new form of recycling, that is, they can make radiation shielding tiles out of this plastic and put it on the walls of ISS. And for your information, plastic is one of the best radiation shielders that we have because of the hydrocarbons present in it. After going through, I guess, 20-25 research papers, I have compiled some limitation and some challenges of these processes. So the first one is the lack of standardization. Because since this process is quite new, not a lot of research has been done on it. So like other processes where there are internationally recognized standards, that just lacks over here. But organizations like ASTM and ISO are worked on it, and I've even made committees like F42 or ISO TC 261. And even ASME has worked for it by coming up with a code of conduct of product definition for AM, which actually describes how a particular product should be designed while you're working with AM for industries. And another problem with this is that if you're working for aerospace, it requires strict regulations because a lot is at stake, so it needs to be perfect. Hence, standardizations again comes in place. Second is the process parameters. So since this process is new, you don't know what's going to affect it. How much the temperature should be, how much the laser how much energy should be concentrated at what amount of length, what should be the speed. So a lot of things depend upon that, and a limitation is that since industries are working on it, they are keeping everything confidential for their own profits. The third one would be the defects. That's there with almost each and every kind of process. And to get to know about the defects, you need to improve your inspection techniques, and that also lacks in this kind of a process, because if you're making complex shapes using AM, then the internal structures might interfere with the non-destructive techniques. And I guess till now the only possible method is using CT scans, which works effectively. And also, if you're using a component, you would like to test it in the actual place where it would be used. And if you're talking about aerospace, it's really difficult to use a part over there. So that's another, I guess, disadvantage. And the main kind of defects that we see in used parts would be layer-to-layer adhesion, where the layers might not stick together, porosity, which are the small holes or even larger ones while making a component, or bad surface finish. Now we're talking about the advantages. So let's come to the first one over here. Yeah. It's possible to make really complex geometries that's not possible by other methods. What we have over here is a rocket engine that's made by a startup called Cellco in Berlin. So they have achieved such a complex design of a single body rocket engine with such, what you see over there, those pipes over there, they are cooling channels, which you cannot make with any other process till now. Another thing, it's really economical and eco-friendly, which are the current top requirements for us as the inhabitants of this earth. So economical, well, as you can see over this graph, it cannot compete when it comes to mass productions. But when we talk about lesser amount of products, it's the best we have. because the amount of customization option it makes available for us. And in this graph, as you can see, for the particular the cost of each component remains same, while when you're talking about product on a process called injection molding, the amount overall amount reduces as we create more and more amount of products per part. Also, if you're talking about eco-friendliness, since you're reducing the mass, so while launching it from Earth to the space, since the mass would be lesser of the components, the fuel requirement would be less. Also, since the scrap material generated over here is really less because of less machining, it contributes towards less wastage. Now here we have a case study which is of Airbus A320. Now what you have over here is a bionic partition which separates the crew cabin from the passenger area. So using this design, what they achieved was reduction in mass by 45%, reduction in strain by 8%, and reduction in CO2 emissions of the single aircraft by 465,000 metric tons by using a single partition on board the aircraft. And how did they make this? Such a complex design. Just look at it. How did they make this? It was possible using AM. This design was inspired by slime molds, how they grip to their surroundings, studying their algorithms, and by bone of the mammals, where the density of the bones is high at the junctions. Now we need to think about the future scope. We know what it is, level it is at currently, but what can be achieved with it in future? The opportunities are endless. The first one is the biomedical applications. What about 3D printing organs? We're experimenting with it, but we're not there yet, but it's really possible in the future. Second would be in-space satellite manufacturing. Imagine you don't need to launch your aircrafts. You can just, build them in space. There was a photo about Archinaut, which is an initiative by NASA and a company called Made in Space to manufacture in space, and it might be possible to make CubeSats, which are really small satellites in space. So, well, it would be really crucial for Earth independent colonies in future to set up their infrastructure using this. Third would be the next one would be self-replication. Using AM, a machine would be able to build its own parts and maybe make others like itself. Also, the last one would be cheaper and cleaner aerospace transportation. As I discussed in the earlier slide, how it is able to reduce the carbon footprint around the world and also reduce the scraps, and that is the need of the hour currently. Now moving towards conclusion and discussion of this entire presentation, what points that I feel are the main points where I need to focus about this technology after going through a lot of research papers. So what I think we need is currently is the gradual variation from subtractive and the other convention process to additive manufacturing, so that both the parts can work in sync. So we have a lot of subsystems in a system, so we cannot directly make the entire thing with additive manufacturing. We can move from smaller parts to the other parts, and maybe then in the end, I guess a decade or so from now, all the parts can be made using a single process. But right now we need such an interface where the parts made from both the processes can work in sync. Second would be we talk about confidentiality, right? So right now on an international level we need collaborations between institutes, researchers, governments and industry, so that this technology can be processed further and there's more material available online. Then there's need to be a top-down approach now. We need to we need to focus on increasing the functionality by a particular design, and then work towards topology optimization of it. The fourth one would be we need to research upon improving the surface finish, because that plays a key role while talking about the fatigue failure of a component in a place with high amount of vibration, which will be there while talking about aerospace. You might ask, what is fatigue failure? Well, fatigue failure is the failure of a material which is caused by a fluctuating load, such kind of a situation. And with this, I would like to go towards the next slide, which are the references which have really helped me throughout this presentation. And I really thank them for this, because I guess the next research project of mine would be in the same field only. Now, going with the references. And with this, I would like to end my slide. Thank you so much.